Okay, let's look at a couple examples that you are going to encounter in the homework, and then I will turn you loose to tackle 1.4. Okay, so let's start with this example. We've got an A matrix and we've got a B vector. And the question is the matrix equation AX equals B consistent for all possible values of B1, B2, and B3? Another way to say that, of course, we know from last video, would be do the columns of A span all of three-dimensional space, all of R3? Can you get to any point with three coordinates by combining those three columns? So this is the way it's actually asked in the question. Let's get on the right layer. But we know an equivalent statement is this one. Do the columns of A span three-dimensional space? So we still really only have one tool for doing that, which is row reduction. So let's go ahead and see what we can do. The original matrix would have to look like 1, 2, negative 2, B1, 2, 7, negative 3, B2, and 1, negative 1, negative 3, B3. And since I already recorded this video once, I have some of the steps written out already. But think about what we'd be doing here. The normal row reduction algorithm would say first thing you're going to try to do is put a 0 here and then a 0 there. And that would be adding negative 2 of row 1 to row 2 and adding negative 1 of row 1 to row 3. So those are the first two steps I've mentioned there. And I think I can do both of those as I write down the matrix. So the top row will stay the same. Adding negative 2 of row 1 to row 2 would be negative 2, so 0. Negative 4 plus 7 would be 3. Positive 4, negative 3 would be positive 1. And then negative 2 B1 plus B2. Okay, and likewise we're going to do negative row 1 added to row 3 to make row 3. Okay, so that would become 0, negative 2, negative 1, negative 3. Positive 2, negative 3 is negative 1. And negative B1 plus B3. Okay, we got zeros in the first two spots. I still need to put a 0 where this negative 3 is right now. So that would simply be adding row 2 to row 3 to make the new row 3. So that'll be our final step. So 1, 2, negative 2, B1, 0, 3, 1, negative 2, B1 plus B2. And okay, adding row 2 to row 3 to make row 3. So 0, add to 0, 0. 3 and negative 3 is 0. 1 and negative 1 is also 0. And adding these two together would be negative 3 B1s plus B2 plus B3. Okay, so the question here was, is the equation AX equals B consistent for all B1, B2, B3? Notice that we did not have a pivot in the third row. So think back to our four equivalent statements. It's false that we have a pivot in all three rows. So it's also false that AX equals B is consistent for all values. It's also false that you can't that you can combine the three columns of A to make any B. So generally false. And just to go all the way back to the beginning of what we know, is this will be inconsistent if we have 0, 0, 0, not 0 in the augmented matrix. And it's certainly possible to pick the right B1, B2, and B3 so that this does come out 0. There are certain values of B1, B2, B3 that you could solve this for. But there's lots of ways that B1, B2, B3 is not 0 will not make a 0 in this spot. For instance, if b1 is 0 and b2 is 1 and b3 is 1, you'll get 0, 0, 0, 2, which is unsolvable. 0 of x1, 0 of x2, 0 of x3 equals 2. Can't be done. So apparently 0, 1, 1 would be a vector that you cannot reach by combining the columns of A. There are others that you can. 0, 0, 0 comes to mind right away, but any way that you can put b1, b2, b3 in here and have this come out to be a 0, then you have infinitely many solutions, right? You have a free variable. Okay, so there's a question in the homework that's pretty similar to that one, so I just wanted to let you get familiar with that. And the other thing that I wanted to point out is that there are actually two different ways to compute a matrix times a vector. There's the way that we started these 1.4 videos with, which is kind of the definition of matrix times a vector. So let's do that one first. And that's just to say the vector tells you how to combine the columns of the matrix. So this vector starts with 4, so let's say 4 of the first column plus 3 of the second column. Plus 7 of the third column. And then you just multiply first and then add, normal order of operations. So this would become, first vector would become 4, 0. Plus 6, negative 15. Plus 14, negative 35. Yeah. And then you just add them up. So let's see. Something seems wrong. Oh, that's not negative 5. That's 3. Sorry. Hope you're taking your notes in pencil. Let's see, I need a small eraser. So yeah, this is not negative 5. That was actually... Oh, and that's not 2 either. Good gravy. You'd think after I'd done this twice, I'd get it right. Okay. Sorry, that would be 7 times the third column, which happens to be negative 1, 3. There we go. So let's erase that stuff and try this again. Okay, I better make sure my other one's right. Okay, first column 1, 0, second column 2, negative 5, and 4 of that, and 3 of that. Okay, that looks good. Okay, let's finish this third column. This would be negative 7 and 21. Okay, that feels a little better. And then let's add them up. 4 and 6 is 10, and negative 7 would be 3. And then 0 and negative 15 is negative 15, plus 21 is 6. So the ultimate result of multiplying this matrix by this vector is a way of combining the 3 columns, and we ultimately end up with a vector 3, 6. Okay, that's fine. So that's one way to compute a matrix times a vector. The other way is to say, hey, let's just do the top entry first. Let's just focus on getting this 3. And notice what happens is the 4 gets multiplied by the 1. The 3 gets multiplied by the 2. The 7 gets multiplied by the negative 1. So they're just saying, hey, let's jump right to doing that. So it's going to be 4 times 1 plus 3 times 2 plus 7 times negative 1. That's the top entry. And the bottom entry, well, let's finish the top entry. That'd be 4 plus 6 is 10 minus 7, 3. We already knew that. And same thing with the bottom. It'd just be 4 times 0, 3 times negative 5, and 7 times 3. And we know that's 4, and it's negative 15, or sorry, 0, and negative 15, which is negative 15, plus 21, which is 6. So it gets you to the same place, and it gets you there by doing the same computations. It's maybe slightly less writing, but both of these methods will be useful to us. In this particular example, which is pretty small and had all fixed numbers in it, either one's pretty easy. Later on in the course, where the entries of the matrix are not numbers, but they're letters or even other matrices, sometimes one of these will be more efficient than the other for us. So at this point, I really want you to be comfortable with both methods. So practice them both. I think your very first homework question asks you to do this both ways. And again, as much as the more time you spend now getting comfortable with both of these ways, the more pain you're saving yourself later. Okay, with that, I will turn you loose on the 1.4 homework. You are ready to go. As always, if you are tackling the homework and you have a question, shoot me an email, shoot me a Zoom request. I'd be happy to talk with you.